it's 5 things you must know about Datalink weather. Certainly there are more than 5 things, but I'm going to try to highlight 5 things that come to mind when I teach pilots about Datalink weather. So for those who do not know me, I'm a CFI. I've been a CFI for about 25 years and a former National Weather Service meteorologist. I've been a meteorologist for about 42 years. I'm also a contributing editor for Flying Magazine. And I'm the founder of EasyWX Brief. It's a progressive web app, easywxbrief.com. I'm also the author of the SCUT Log PME, a primer for pilots, and the co-author of Pilot Weather, From Solo to the Airlines. All right, so here's the agenda today. We're going to connect you with convection. That's the key element when we're looking at Datalink weather. Typically, we're looking for an understanding of where there may be convective turbulence. And so I want to connect you with convection. Next, we're going to talk about Datalink lightning. We'll get into the latency of the Datalink radar mosaic, very common question I get all the time. Then we'll get into cloud and echo tops, and then finally service coverage, and at the end we'll take some Q&A. All right, so first up on the list is convection connection. All right, so for everyone out in the audience there, what is the most significant weather threat for summertime flying? I know we're getting into the winter time, but let's talk about summertime flying. And before you answer that, I'll give you a hint. It's not thunderstorms. So yes, thunderstorms are dangerous. I'm not going to downplay that at all, but it doesn't take a full-blown thunderstorm to ruin your day. So the key is to minimize your exposure to deep moist convection, or DMC. That's a term that I would much rather pilots use than the term thunderstorm. I've always said if I could get rid of one word out of a pilot's language, it would be the word thunderstorm, and replace it with 3 words: deep moist convection. And that's what we're going to talk about next. So everybody's probably seen this particular graphic. It was in the Aviation Weather Advisory Circular 00-06 Bravo. And now it's been incorporated into the weather handbook that the FAA put out not too long ago. Nevertheless, this is a common graphic that shows the thunderstorm life cycle: the towering cumulus stage, the mature stage, and the dissipating stage. Nothing wrong with this graphic. It's fairly accurate, but I think the focus when instructors spend time teaching pilots about this, they spend most of their time on this mature stage. And I think that's the wrong approach. I think we should be spending more time talking about the towering cumulus stage, or essentially the beginning of the thunderstorm process. Now, not too long ago, somebody asked me to define what a thunderstorm is. And I thought about that, and I thought, well, I can come up with a definition pretty easily. It shouldn't be too difficult. And I came up with 3 or 4 or 5 definitions. I really didn't like any of them, to be honest. But I did find one on the National Severe Storms Lab website that defines a thunderstorm as, and you're going to probably chuckle when you read this, a rain shower during which you hear thunder. Since thunder comes from lightning, all thunderstorms have lightning. The key is that first part of this definition, a rain shower. That's the key element that I think most pilots are not taught when it comes to the concept of convection here. So all thunderstorms, big or small, supercell or pulse type thunderstorms, air mass, all begin as a rain shower. And not all rain showers grow up to be full-blown thunderstorms. So the rain shower in that definition is just the beginning of that convective process. In that thunderstorm life cycle, it's that towering cumulus stage, essentially. So rain shower is just the beginning of the whole convective process. And so looking at this picture here, this is a supercell thunderstorm in the high plains. How many of you would make a hard right turn into that shelf cloud and fly into it? And I'm sure nobody is raising their hand that says, yes, they will fly right into that supercell thunderstorm. Why not? And I usually get a lot of different responses like, well, convective turbulence, you'll die, lots of things. Really need to even step way back. Don't overthink this question. And the reason why you would not turn that way is because it looks threatening, period. Nobody's going to go there because it looks nasty. So I'm sure a lot of you out there remember a fatal accident of Delta Flight 191 at DFW back on August the 2nd, 1985. Very tragic accident, but that accident sparked a lot of study and research into the notion of what I'm going to be talking about. So was this accident caused by a supercell type thunderstorm? And the answer is it was not. There have been no airline accidents caused by a supercell thunderstorm. So let's look at the conditions just before, 5 minutes before this accident happened. The accident occurred at 6:05 p.m. Central Time. And so here was the observation from a trained observer 5 minutes before this accident occurred. 6,000 foot scattered clouds, estimated ceiling was 21,000 foot broken. Visibility was an amazing 11 miles. Not bad for a August 2nd situation. Wind, nothing to really speak about here, 120 degrees at 8 knots. Temperature, ouch, 101 degrees Fahrenheit with a dew point of 65. That's certainly interesting. Well, that temperature dew point spreads a little bit of a hint there, which we'll talk about in a bit. And it said the actual observation mentioned cumulonimbus thunderclouds north and northeast, which means that they're more than about 15 miles away from the airports. So does any of this look threatening? Again, 5 minutes before this accident occurred. And most pilots would look at this and say, this looks actually a pretty good day to fly. Light winds, great visibility, no real clouds to deal with, no precipitation, no thunderstorms. Some thunderstorms in the distance, not that big of a deal. So it doesn't really look threatening. However, this situation, 5 minutes after this situation occurred, an L-1011 crashed short of the runway. So some of you may know the name Fujita. Dr. Ted Fujita was the scientist that worked at University of Chicago and kind of was a pioneer for understanding microburst activity. And him and his good friend Fernando Carosina, recognized experts in this particular field of microburst, even before this accident, repeatedly emphasized that microbursts are frequently generated from benign appearing cells. And I'll read that again. Microbursts are frequently generated from benign appearing cells. So you see there are the mature thunderstorms out there that were north and east of the airport. And you see here the DFW airport, not much in the way of a satellite signature at all. However, At about 6:05 p.m., there was a microburst ongoing near north of DFW itself. So again, this is a pretty benign looking situation, but this particular cell, not a supercell thunderstorm, caused this accident to occur with a microburst. So again, let's look at another situation. This is out of Chandler, Arizona, where microbursts frequently happen. Does this situation at all look threatening? It doesn't really look all that threatening. You look around, you see some blue sky, maybe a little bit what may look a little bit like Virga or haze, but this doesn't really look all that threatening. And certainly, obviously was taken from the ground, this picture, but imagine you were headed to an airport underneath this area. Again, this situation doesn't really scream of danger. But we'll see, a little rain shower may not look very threatening, but it can still be just as dangerous as that supercell thunderstorm because it lures you into thinking it's safe. So let me show you this video. And I'll run it through a few times so you can see what's happening here. Once again, this is about a 20 to 25 minute lapse, time lapse, and you can see how that microburst occurs. Looks pretty benign, and all of a sudden you see a downburst of precipitation coming out of that cloud. Now, the key here is when you look at this is that the bases of these clouds here are well over 8,000 feet, probably closer to 10, maybe even 12,000 feet above the ground. And the same thing we saw with the DFW, we're talking about 21,000 foot broken. So in this particular situation, we're looking at high bases, usually dry conditions below the cloud base. And those are conditions that are ripe for a microburst encounter. But again, this is a benign cell that produced a microburst here. This is probably a microburst that's, I would say, is a more minor one, but I definitely would not want to be under that. Certainly not trying to fly into an airport and land in that situation. All right, so I was making a flight from Charlotte Douglas Airport, where I live, to Birmingham, Alabama. And I turned on all the good stuff, like the reflectivity. So you see the NexRad mosaic there. I turned on the lightning, and I verified that by looking at other places where it was definitely shows lightning. But there's no lightning being shown anywhere on this particular screenshot. That's because none of these cells that you see here, these are all cellular appearance, don't have any lightning in them. These are rain showers. You technically can't call them thunderstorms. So it's important to understand that you can't use lightning as a determination whether it's safe to fly through or under a cell. You really need to see and avoid. And certainly if there is lightning, that's a good indication you've got some really cold cloud tops, which we'll talk about in a bit. So make sure that you also have these storm tracks, as well as these echo tops, depending on what particular app that you may use, because in the event you want to still see those because they define where there are well-defined cells. And that's a good indication you've got a convective process in place. So everything you see here is basically a rain shower. So showery precipitation, any forecast that you see for showers is a forecast for convection. The word showers should be equated to convection. So that includes forecasts like showers in the vicinity, VCSH, and rain showers in the terminal area itself, that's that 5 statute mile area, SHRA. Both of those are clear indications that a convective process is in place. And I don't care whether you're listening to your local TV broadcaster, you're reading some discussion on weather. If showers is mentioned, that really needs to trigger in your brain that we're talking about a convective process in place. So you notice here that this is a line from a terminal forecast, SHRA, and you notice there's no CBs or cumulonimbus clouds on the cloud group. Certainly if this were TSRA, they would put that on there. But that's not the case here. So there's no real hints to the average pilot that this is a convective situation. In fact, it may even be an embedded convective situation, noticing that we have a broken 700, overcast 1500 ceiling. Likely we potentially be dealing with embedded cells. So showery precipitation is sometimes used by meteorologists as a placeholder for a low confidence thunderstorm event. So when forecasters in a situation where you may have a lot of hit or miss kind of afternoon variety thunderstorms, we call those pulse type thunderstorms in the meteorology business, those don't necessarily cover like a long line or a big area of thunderstorms, so that forecasters can get a pretty good confidence that, hey, this terminal area will be impacted by thunderstorms. So when we have that hit or miss kind of cell, forecasters often throw in the shower, either rain showers in the terminal area or in the vicinity, to cover the threat of thunderstorms. So I'll give you an example. That particular flight I was taking from Charlotte to Birmingham, I pulled up the area forecast discussion, which you can get from some of the heavyweight apps out there. And it says scattered showers and perhaps a thunderstorm are expected across the North Carolina Piedmont from the afternoon until early evening, and will carry VCSH for now to cover that threat. So it's real important to read the area forecast discussion. It kind of fills in, when you're looking at a TAF, for instance, you're only getting about 50% of the information. The area forecast discussion sometimes goes into details about why they added showers into the forecast. And this is very clear what's happening now in this situation. All right, so let's move to the next topic, and that is Datalink lightning. Datalink lightning. All right, so the presence of lightning, so when you see lightning either on your Datalink weather or in some other app, you know that you're dealing with very cold and likely high, tall, convective cloud tops. And that implies a significant vertical mixing component to this, and that's going to cause the potential for severe or extreme convective turbulence. So lightning is a definite indicator to stay away. But remember, not all convection has lightning. But when it does, it's also indicative of low-level convective wind shear, which may not necessarily be right under the cell itself. We have outflow boundaries, gust fronts, all are a result of convection. And so that low-level wind shear may actually be 5, 10, 15 miles out in front of the main core, main cell that's causing it. So lightning comes in two different flavors: cloud to ground and intracloud, or what some would call cloud to cloud lightning. Meteorologists like to use the term intracloud lightning. And you can see here in this cell that there's a lightning bolt, and that cell doesn't really look all that nasty, but here's a lightning bolt coming out of the cell itself and striking well beyond where that particular that cloud is located. And this is a bolt out of the blue. And so these kind of strikes can actually happen fairly frequently, where you're not really under the cell itself. It can be up to 5 to 10 miles away from the cell. And I've visually seen these myself, and it'd be kind of surprising that this can happen. So this is my public, kind of a announcement to, as being part of the Weather Ready Nation of the National Weather Service, being a sponsor for that, is that if you can hear thunder, you can be struck by lightning, plain and simple. So the old adage, when thunder roars, go indoors. So if you're out pre-flighting your airplane and you hear thunder, maybe you should take and wait it out before you finish your pre-flight and get inside where you're protected. And just to re-emphasize this a little bit more, this is a tree that was hit by lightning, not this past July, but a year prior to that. And this is in a park in my neighborhood. And just to the left of that is our community pool. And this was the second tree that was hit at this particular time. It was the second tree that was hit and had to be cut down. You can see, if you look at this really carefully, you can actually see that there's daylight that you can see between it. This was a negative lightning strike that hit this. That only lasted 92 milliseconds, pretty quick, but it pretty much destroyed that tree and blew the bark off of it that landed about 100 feet from the tree itself. As the moisture in that bark boiled immediately, causes this explosion, and that's what we see here. And this tree had to be cut down. I was in my office here, and it's one of those scenarios where the lightning occurred and immediately you heard the thunder, so you knew it was close. And so I'm looking at the ground-based radar on my radar scope app, and the nearest cell that this was generated from was 10 miles away. So a bolt out of the blue, there was no rain, no precipitation that occurred at all at this location. And of course, our Facebook page lit up in our community, and they said, "Hey, a tree was hit near the pool." And so the weather geek that I went down there once the storm had moved out, far enough away, and took some pictures of this. Well, needless to say, this past June, another tree was hit by lightning, and you can see the stump there on the right, lower right. That was the tree they had to cut down. So yet another tree right next to it was struck by lightning, and that had to be cut down as well. So that makes 3 trees within the same like 25 yards. And oh, by the way, the tallest of those 3 trees that were there didn't get hit. So the tallest object is not necessarily the actual target. So 3 trees. So the moral of the story is, and if there's any hint of thunderstorms, I don't go to this park. So let's look at the broad perspective of lightning in terms of intracloud or cloud to ground. So if we look at the ratio of intracloud lightning to cloud to ground lightning, what you'll notice is that here in the central part of the country, you're dominated by a high ratio. So in other words, about 10 intracloud strikes to cloud to ground strikes. If you're here more in the eastern U.S. Or even in the mountains, the Four Corners region, or along the Sierras, it's more of a 2-to-1, maybe 3-to-1 ratio. So there's a lot of situations where you see intracloud lightning over cloud to ground. In fact, many severe storms with that high flash rate are dominated by intracloud lightning. Often more than a 10-to-1 ratio. And in some of the most severe storms, you can actually have an infinite ratio, meaning that it's all intracloud lightning and no cloud to ground lightning. So therefore, it's really important to be able to see both of these, both cloud to ground and intra-cloud lightning. If you're not seeing both, you're potentially missing some aspects of the weather. So it turns out that ADS-B, FISB, only broadcasts cloud to ground lightning strikes. So in a developing storm, that rain shower we talked about, most of the time, intra-cloud lightning dominates the cell itself. And so SiriusXM, on the other hand, provides both of these, both intra-cloud and cloud-to-ground lightning. And certainly if there's a well-defined line and it's of mature cells, you're going to see, most likely you're going to see cloud-to-ground and intra-cloud lightning associated with that. But go back to what I said earlier, that those benign cells are the thing that's going to bite us in a supercell type thunderstorm. We're going to stay away from those supercells, and we're going to stay away from these areas where there's a well-defined line of convection. But certainly the fact that you want to see both so you get the best picture, and SiriusXM certainly provides that. All right, so let's talk next about the latency of the Datalink radar mosaic. It's probably the most common question I get when I do these presentations at Sun and Fun or Oshkosh. And so the age-old debate is, what is the age of the broadcast you're getting? Well, we know that it's not real time. If I told you it was real time, I would be doing you a disservice. We know that the broadcast, the mosaic you see on your iPad or on your multifunction display is not real time. The only way to get real-time information for radar is if you have an onboard radar itself. You have a pod, and that way you can scan the cell itself and see what the reflectivity is. So anytime you receive data in the cockpit from the standpoint of the radar mosaic that you see, it may not reflect what you see outside the other glass. It's not the glass in the cockpit itself, it's the windscreen. So it's really a glimpse of the recent past. So when you're looking at the data on your iPad or on your multifunction display, you're really looking at what's happened in the recent past. The problem I see, and I see this thrown around a lot on the internet, on various different Facebook groups, is that they look at it and say, no, it's the idea here is that the data link latency is 20, 30 minutes sometimes, I read. So the NTSB put out a 3-page safety alerts, and you can read it here at that particular link. And here's the key element is, although such situations are not believed to be typical, in extreme latency, the age of the oldest NexRad data in the mosaic can exceed 15 to 20 minutes. And what everybody sees is that big, bold red area, 15 to 20 minutes. And at that point, everybody thinks that the NexRad mosaic you see is 15 to 20 minutes old, and it's not. To say that the NexRad image is 15 to 20 minutes old typically means that you've missed some updates. But to say that that's what I see on a regular basis, in terms of expectation on a regular basis to be 15 minutes to 20 minutes old, it would be the same thing if I told you it was real time. I think that's doing a disservice. So let's talk about the age aspect of this. So there's really no way to determine what the age of that mosaic is. You may see something, for instance, on your screen. So if I'm pulling up Garmin Pilot and I look and see when the last radar mosaic that I've got, my composite, it says it's 3 minutes old. Well, that's just showing you the receipt of the broadcast. It doesn't tell you what the age of that radar mosaic is. So let's talk about the latency aspects of getting that radar mosaic, and there's 5. First of all, there's the volume scan of the individual radars. It's approximately about 5 minutes. Now, get into this a little bit more detail in a second. And so it takes 5 minutes to scan the entire volume of the airspace. So the radars are doing many sweeps and many elevations. And when they finish that scan, and that's available for a composite, which is the worst case scenario in the entire column of air, and that's the pixel you'll see at that particular location. Then it takes some time for it to composite all this and do ground clutter filtering, and then ship it for Sirius XM or Harris for to be broadcast, and that's less than 20 seconds. It's pretty minor. And then it takes time to uplink. We have to do bandwidth scheduling. We can't just broadcast it when we're done, so it has to be scheduled so it maximizes the bandwidth that we have available, either in FSB or Sirius XM. And then it takes some time to render it on your display. There's a software on the other end that's got to take all those packets coming in and put it together. And if it all comes together, then it goes out onto your display. And if it's out of order, in some cases, you may have to deal with that. You may have to wait a little bit. So it takes some time to render on your display. And then you have the stare time. You look at that thing for 2 minutes for FSB and 2.5 minutes for Sirius XM. That's minor. It used to be longer, 5 minutes, but now we've cut that down to 2 minutes and 2.5 minutes. So the stare time is less than it was years ago. So when you look at your either, in this case, Garmin Pilot, and I'm looking at each individual pixel, you don't really know what the age of that is. So one pixel may be 2 minutes old, another one may be 3 minutes, and another may be 5 minutes, because it's using a composite looking at all elevation angles, and it's stitching all this together, and that's what you get. And that gets shipped out. There's a little bit of delay. But again, you don't know specifically what the age of that pixel is. You got to make some assumptions. So I always tell folks to think about it as once it hits your receiver, you're looking at 3.5 minutes to maybe up to 7 minutes old for any of those pixels. And again, you get to stare at that for another 2 minutes. So it's not real time, but it's still incredibly useful to us. All right, so let's look at the next topic, and that is Datalink Cloud and Echo Tops. Yeah, another question I get is, Scott, tell me a little bit about how I find the tops. It's sort of the holy grail, if you will, for pilots, especially instrument pilots that want to pop out on top and stay on top, and that way they can stay out of any, and they can have good visualization of what's happening along the route, and they can stay out of icing if there's icing issues. So they really want to know where the tops are. So ultimately, knowing where that top or that cloud deck is really can be a benefit to you pre-flight, but also while you're in flight. There are generally two different flavors of tops. You can see Echo Tops. That comes from NexRad, and only Sirius XM broadcasts that, or Cloud Tops, and you get a broadcast for that from both Sirius XM and FSB. Now let me explain a little bit about Echo Tops, because I still think this is a pretty good product to be looking at. And again, only Sirius XM provides this out of the two services. So when they sew together that mosaic from all the different NexRad sites out there, one of the products they look at is the Echo Tops themselves. And so it represents the altitude of the top of the precipitation core. And so the tops represent the mean sea level height of the tallest echo that's 18 dBz or greater. So whatever the tallest is, that's the echo top height. So here's a situation where we have a slice of a thunderstorm. So thunderstorms cut from one latitude, longitude to another. So we're kind of slicing it along that area. And so if you were to look at the 18 dBz, which is somewhere in this blue area, and you were to find where the top or the maximum is there, that would be the echo top height of that cell. And so in this case, it's roughly around 56,000 feet at this particular location, maybe lower at other locations. So this gives us a very good way to determine where the top of that precipitation core is located. The higher the tops, the more typically the more severe or more significant the cell is. And so when we start seeing echotops above 40,000 feet, we know that that represents pretty significant convection, and therefore we need to give it a lot more breadth in terms of understanding how to get around it or circumnavigating that area. So again, the echotops is really only about convection. So it's only used to determine the extent of convective precipitation. So it's not really used to determine the top of a stratus deck, because usually stratus clouds don't provide you with any kind of precipitation, maybe drizzle. But if you have a stratus deck that goes up to 6,000 feet in the tops, you're not going to see any precipitation out of that that's significant enough to show up on radar. So you're not going to see any echotops from those kind of things. So we're only really talking about convective precipitation, including what I talked about earlier, showers. So when you look at the Sirius XM echotops, make sure you have the lightning turned on. Here it is shown as Garmin Pilot. We have lightning turned on with the echotops. And that kind of gives you a way of looking and understanding where the most significant cells are located there. And also, if you can, if you have the ability, make sure you overlay convective sigmets. So convective sigmets, you can see, are also a good way to understand where the true threats are. If there's a convective sigmet, forecasters have determined that this is significant for aviation. Now, you can probably pick your way through some of this, but ultimately, we see the echotops are on the higher side, and we can see that we have the lightning there. All of those defined exactly where the most serious weather is located. And so you have to understand the coloring, the grayscale there to know where the tops are. And a lot of products also allow you to cursor over those and see that as well, depending on the application or multifunction display you're using. The other thing I mentioned earlier is the storm cell attributes here also give you information on the tops. So you can see, and again, these are based on echotops. So you can see 30,000, 25,000, 20,000, even 35,000 over here. So that gives you, again, the indication where the truly ugly stuff is out there. So it helps identify where those cells are you need to stay away from. So anytime you see those tracking cells there are generated by the NexRad site themselves, and they're pulled in and shown here for the Sirius XM. So ultimately, they also give you a lot of information about what the cell is doing. So the higher that number, the more significant the cell. And again, you want to stay away from those cells, even if there's no lightning associated with it. Now, cloud tops are kind of a weird thing to deal with here. Ultimately, when we look at cloud tops, we're talking about the highest layer of clouds. So there may be multiple layers, a lot of nimbostratus kind of scenarios where you can have tops at 30,000 feet, have multiple layers of clear air in there. And so it's hard to figure out what that means from a top. So if I get a top of 30,000 feet, but I may be able to fly fine at 12,000 feet in between layers and not be in any cloud, that can happen as well. But tops are really to talk about the highest layer of clouds. And so both SiriusXM and FISB broadcast cloud top information, but there's one critical difference between the two that I think is really important. And that is above 5,000 feet AGL, SiriusXM broadcasts the actual cloud tops. And that's based on satellite imagery using cloud top temperature. If we know the temperature of the cloud top, which comes from satellite information, we can then look it up and say, well, based on that temperature, where is the temperature aloft? What height is that particular temperature aloft? And therefore, we can infer what the cloud tops look like. So this is more actual cloud tops. whereas FSB broadcasts a 1 or potentially 2-hour forecast of cloud tops from the high resolution rapid refresh or HER model. So again, FSB broadcasts a forecast of cloud tops. And we know forecasts are not observational data. Certainly observations go into the forecast, but ultimately there can be some big differences using actual cloud top information, which is what happened in the recent past. We're not talking about real-time cloud top information, but within the last 15 to 30 minutes. But the broadcast from FSB is a forecast. And so here's an example where the HER model really had a pretty big miss. And so what you see on the right is the actual radar mosaic valid at 14Z. So at 14Z, this is the radar depiction. And I don't have a image of the cloud tops from the HER model here, but I pulled up the what's called the forecast radar depiction on the left there. And you can see that over northwest Louisiana, there's nothing showing there. But you can see on the right, there was definitely some convection in that region. So the model itself wasn't really handling this convection at all. That returns that you see on the right were really there. That's the actual returns. And the model didn't pick that up for whatever reason. So again, using a case where you have a model forecast, it's going to miss a lot more than using actual information. So I prefer to see the actual cloud tops rather than a forecast for it. All right, last but not least, let's talk a little bit about service coverage. So really two categories to speak of, and that is the reception of the broadcast and its limitations between ADS-B and SiriusXM. Now, ADS-B was designed for aircraft flying below 24,000 feet. Now, certainly, it's not saying that you can't pick up the signal and can't utilize information if you're above 24,000 feet, but they don't broadcast turbulence above 24,000 feet because, again, it's mainly looking at what's happening below that amount, below that altitude. And then you also have the coverage map. You can see on the right at the top is ADS-B coverage. So once you get out of the United States, you start to lose coverage pretty quickly in terms of being able to pick up the signal itself, where SiriusXM has a really good coverage all the way down from Mexico, a little bit parts of the northern part of the Caribbean, and then all the way up in through Canada. So if you happen to be crossing over the border up into Canada, SiriusXM is going to give you that coverage in that area. It's also going to provide data in that region as well, whereas FSB is basically a US-centric product. All right, so FSB is subject to a line of sight restrictions. And that means that if you can't see you can't pick up the reception for the tower that you see there on the right, you're not going to be able to pick up the broadcast. And there are some low-tiered ADS-B transmitters at some airports. My home airport of Rock Hill, South Carolina, has one. So you can get data, a fair amount of data before you depart, but a lot of airports don't have those. More of the major airports do, but not all do. So ultimately, if your airport doesn't have an ADS-B transmitter, you're not likely to receive the broadcast until you've climbed out of the traffic pattern altitude, or sometimes higher, depending on what the terrain is around you. In the mountainous regions, you may have to climb much, much higher to start picking up at least one transmitter. So that's not a problem with SiriusXM. In this case, with SiriusXM, as soon as you pull your airplane out of the hangar, you'll start receiving the broadcast. There's no really line of sight restrictions except a line of sight to the sky. And so a lot of times what I'll do is when I'm going out to pre-flight the airplane, I'll turn my GDL 52 on and I'll connect it up to my Garmin Pilot. And while I'm doing the pre-flight, it's getting all of its information and I'm ready to go when I crank the engine and get in and go. So SiriusXM doesn't have that line of sight restriction that FSB does. Gives you a lot better feeling for when you depart. ultimately, I want to make sure that when I'm departing, if there's some weather like you see out there in this particular scenario, I know there was out of Rock Hill here, there was some thunderstorms and some convection in the distance. And when I want to go depart at this point, I don't want to have to be flipping between internet and also into my Frisbee. In this particular case, I was using SiriusXM, and it's a very, very clean transition from departure up into your planned altitude. So again, the most significant differences between SiriusXM and Frisbee is this service coverage. So with Frisbee, there's this thing called look-ahead distance, and it depends on the product. It also depends on the tower that's sending it. Really hard to really understand to get your head around. But ultimately, there's a look ahead of 150 miles, 200 miles, 250 miles, even 1,000 miles. Whereas SiriusXM provides a pretty simple answer to the problem, and that's a coast-to-coast depiction of the weather. There's no issue with respect to this look ahead. And so when we look at, for instance, the CONUS National Low Resolution Composite Reflectivity Mosaic from Frisbee here, it's transmitted every 15 minutes. And if you look here on the right, you'll see it's a very blotchy, very low resolution product because you're far enough away that you're now out of the higher resolution product. So in a sense, you don't really get a good resolution of the cell that's out there because you're too far away from it. So it's subject to that look-ahead distance of 200 or potentially 250 miles. Whereas the regional composite reflectivity that you see here closer to the airplane here, that's a higher resolution than the national mosaic. So it's going to have, it's going to look a lot more what you expect. And that's transmitted every 2 minutes. It's the MRMS, multi-radar, multi-sensor product from the National Weather Service. But it's subject to a 150, 200 to 250 mile radius around the airplane. So ultimately, you can see the difference between the two. You don't have that issue with SiriusXM. And so here's a case where I was at Rock Hill, which I mentioned. It has a tower on the field, so I can start to pick up the Frisbee radar depiction, but it's a surface base, so I don't get much beyond that. So I'm really limited to what you see here, which is not much. And I'm going to my Birmingham airports on this particular trip, but I prefer to see the picture that you see here with SiriusXM, which gives me a much more indication that, wow, this here earlier, when I showed you here, looked reasonable. But when we looked at the SiriusXM, that route has a lot of potential issues. So again, I want to make the best decisions as early as possible. And SiriusXM gives me that. And SiriusXM's national mosaic here is transmitted every 2.5 minutes. And again, it's a coast to coast. You don't have that look ahead problem. And certainly, if you are not in a situation where you have a tower at your airport, transmitter at your airport, then you won't be able to get this information up into the air and start receiving that transmission. All right, so that's all I really have to say here. Here's my SKU-T log PME, a primer for pilots book. If you're interested in learning more about the SKU-T log P diagram, I have ebook and a physical soft cover book on sale. And my website is easywxbrief.com. There's a 14-day trial if you're interested in looking at that. And there again is the URL for the SKU-T book. And if you have any questions or doing any specific training for aviation weather, you can reach out to me at support@easywxbrief.com.